Well, thank you, John. Before I get started on a couple of comments, how about a round of applause for John and everyone at the Water Resources Center staff that has put this event on today. And I'll just start out. I've been on the advisory board now for just a couple of years, and it's really been one of the most rewarding kind of like, jobs I've had in my career here. Been in Minnesota for the last 17, 18 years. So it's been a lot of fun, and we do a lot of work behind the scenes as you mentioned, to allocate funds to different research projects, planning an event like this, which I think has been pretty unique and interesting. As I kind of observed through the day yesterday, the amount of community and fellowship that I saw among everyone in this room was really inspiring. A lot of engagement. This is a symposium. I saw idea sharing happening everywhere. If you look at the attendance of everyone who's here, pretty well equal parts watershed staff, city staff, implementers, policymakers, researchers, and it's a group like this is where all that sharing can happen, and I think it's been a pretty unique event in that regard. So thank you all for participating and sharing those thoughts with all of us. It helps everyone do better, right? So with that, I'm going to move into moderating the session. We heard yesterday about a lot of physical and technical aspects of ponds and stormwater work. Today we get to shift into the biological side of things. We have Jacques Finlay from the University of Minnesota here to provide us with some information on pond plants and biota.
Good morning, everyone. Excited to be with you in this incredible two-day pond event. Sadly, I have to leave to teach mid-morning, so I won't be here, but I'll leave you in good hands with the panel to answer all of the questions that you might have, and especially those related to the biota part that I'm not going to talk about, which are critters. So I just want to get that disappointment over with right away. So there are lots of interesting things going on in ponds biologically, and we can't cover many of them here today, but we'll make a good start. So here is the team. We had a recent project that finished up, and I'll refer to that final report. A lot of what you'll see today is arising from that. But in fact, it's building on years of work and multiple projects that we're leveraging to do all of this work. And many of you have contributed to that, so thank you for that. And I'll get started. So start out with an overview of what, some of the big points for the talk that I'm going to give this morning. Ponds are alive, they're living systems, you all know that. If you build a pond or you modify a wetland, things will grow in it. And what grows in ponds can either help you in terms of your management goals, or it can make things a lot worse. And there are some thresholds that we're beginning to see that determine the abundance, the distribution of different plant types. And that's the challenge, is for us to find those and to manage ponds in a way that we can sort of push things in the direction that we want them to go in, and that involves nutrient management both in ponds and in watersheds. So that's kind of a big picture overview of the first part of what I'm going to talk about. Starting out with the role that biota plants in particular plays in stormwater ponds, doing many, many things. I've listed just a few things. You've heard about some of them yesterday, and you'll hear more later today. Plants, shoreline plants affecting wind, organic matter inputs, dissolved oxygen. You heard about duckweed. You'll hear more about duckweed today. All of the important functions that give rise or support ecosystem services are linked to the abundance of different plant types. So that's a sort of a foundational piece of the puzzle. And again, this slide I put here just to remind myself to say that there are a lot of other things growing in ponds that are important and relate to some of those ancillary benefits that we heard about yesterday in ponds. Biodiversity, lots of interest in that, but we don't have a lot of information. Steve McComas is here, though. He knows more about critters in ponds than anyone I know in the area, so he will answer all of your questions in that area. So I'm going to sort of focus in on the problem that has been driving a lot of the work that we have been doing, excess phosphorus. Pond functions for improving water quality. One of the key functions is trapping, reducing phosphorus coming in from stormwater runoff and improving the water that's released downstream. This is some older data. I need to update this plot, but it's a lot of data we pulled together several years ago now from different ponds, different numbers of sites, different numbers of measurements, showing these incredibly high concentrations of phosphorus in the surface water. In the winter under ice, there's no oxygen. That makes sense. In the summer, we see a big peak, hundreds of micrograms per liter phosphorus in the water column in many ponds. Most of the ponds in this data set are older ones, suggestive of internal release. So the concentrations are similar or higher than the runoff coming into these ponds. So that's the problem that we're aimed at, or one of the big ones at least. And a lot of the work that we've been doing, you've heard about some of it yesterday, you'll hear more about it, is bringing together different methods, different ways of looking at ponds, different intensities of data collection to get at some of the drivers of these incredibly complicated systems, right? These are biological, these are ecosystems that are, we still don't have a lot of predictive ability in terms of predicting what they turn into and who shows up in terms of the species assemblage. So I just want to point out, we're using this in the project that I'm going to talk about, a lot of this data, leveraging it, and leveraging funding from multiple funding sources, so we really appreciate that as well. So we've sampled a wide diversity of ponds. Not all of them we've sampled, shown in this picture, but some of them we have, including one that is about 600 feet away from us. So see if you can pick that out if you know this area well. I realized that I'd been here before in 2019 to visit one of these ponds, so I'll show a picture of it a little bit later on. Lots of diversity here in terms of size, shape, vegetation, age, showing up, and all of these things are, making a difference or influencing sort of the dynamics of vegetation and water quality in ponds. I'm going to sort of just boil pond vegetation down to a really unsatisfying kind of lumping exercise of different groups. So, within these four groups, hundreds of species represented, if not more. Duckweed, free-floating plants, we heard about yesterday, really amazing little plant, the world's smallest flowering plant, has a really large appetite for phosphorus, can take it up, store it in its biomass, and exerts really strong impacts on ponds by suppressing oxygen and light in particular. Phytoplankton, you all know algae, sort of at high levels, not such a good thing, greater risks of HABs. Macrophytes, submerged macrophytes, or SAV, are generally the good guys, if they're native species, having positive effects on lakes and ponds. And in shallow lakes, we're managing for macrophyte, sustained native macrophyte communities. Emergent vegetation is also present in our stormwater ponds. I'm not going to talk very much or hardly at all. There are people in this room that know a lot about emergent vegetation, and just for time's sake, I'm not going to talk about the little work that we've done. We've mostly focused on the three other groups in terms of our work. So to start out, and emergent vegetation, I think, also having strong impacts on ponds. To start out, I'm going to show you sort of the data that we've pulled together in the most recent project for different vegetation categories related to mean summer total phosphorus concentrations. So we've shown here are sites dominated by phytoplankton, dominated by duckweed and submerged vegetation, dominated by submerged vegetation, and new ponds. And the thing that you can pretty quickly take away from this is that there's a lot of phytoplankton or a lot of duckweed. We have similarly very, very high phosphorus concentrations. If we have duckweed and submerged vegetation together, I'll show a picture of what that looks like. We see this in a lot of ponds. The benefits of submerged vegetation almost are erased. So we get a little bit more oxygen, a little less phosphorus, but really sort of duckweed is having a negative effect on the function of submerged vegetation. So the winner, of course, is submerged aquatic vegetation, generally having positive effects. So ponds dominated with SAV have a substantial improvement in terms of water quality indicators, this one being total phosphorus. So I'm going to use this slide to try to summarize some of the dynamics, some of them well studied between phytoplankton and submerged plants. And this is a diagram that is showing kind of a little bit of information about the spatial distribution. So duckweed and phytoplankton on top, in the upper water column, shading out submerged vegetation. If we have a healthy submerged vegetation community, we can absorb more nutrient loading at a low algal or duckweed biomass level. Once we cross a threshold and shift or flip the system into a turbid algal or duckweed-dominated system, then we see a lot different water quality expressed in a pond or lake, and we have a lot more difficult time in terms of pushing conditions back to a submerged vegetation-dominated condition. So this is the foundation of what we're after here in terms of looking at the relationships between these three groups in stormwater ponds and edging over into some shallow lakes as well. So you heard a lot about duckweed, and I know you're expecting to hear more about duckweed. So here is a little bit more, and I want to emphasize that the posters are available as well. So those are going to be a good resource for providing more information on duckweed and many other things. So free-floating plants or duckweed, watermeal, and lemna are two really common groups with several species commonly found in stormwater ponds, have the ability to dominate stormwater ponds. And we've seen this through different ways of looking at duckweed abundance. And here is just one example, some data that you haven't seen on one side and some data that you saw yesterday, but you're going to see it again here and probably this afternoon as well. So on the oxygen side, these are data from some surveys. Within a 2-week period, we went out and surveyed a lot of ponds. If the pond is covered in duckweed, there is almost no oxygen, even at the upper surface of the pond. If there is no duckweed, we can sometimes see low oxygen, but it's always higher than compared to the duckweed-dominated site. So duckweed makes ponds anoxic. It suppresses light, which suppresses benthic photosynthesis and blocks oxygen diffusion and exchange. And that makes ponds anoxic, gassy. Joe is here. He's got a poster, Joe Rebay, on this topic from his dissertation. And importantly, this anoxia drives anoxic phosphorus release from the sediment. So here's some data that Purnima has put together comparing duckweed versus non-duckweed sites, with duckweed-dominated sites having much, much higher rates with a lot of scatter compared to ponds without duckweed. So summarizing a lot of information here around duckweed abundance. And now I'd like to shift and try to arrange some information about the abundance of these three groups in space, and using pond area, pond size as a way to do that. So the three groups, duckweed, submerged macrophytes, and phytoplankton, arranged here, with duckweed showing a restricted distribution. As we get into larger and larger ponds, we see a reduction in overall average cover of duckweed, suggesting of a size threshold, which I'll talk a little bit more about in the next slide. Some good news here, we have submerged aquatic vegetation. This is on a scale of 0 to 16 in terms of relative abundance. There is a lot of submerged vegetation present in many ponds that we've surveyed, sometimes at very high levels. The maximum is 16, sometimes at 0, but a lot in between. So submerged vegetation can make it in ponds even though they're warm and don't always have ideal conditions for growth. There are a number of hardy species that can colonize and establish and sometimes even flourish. The last important group, phytoplankton, we see again some size-related effects. So these are ponds without duckweed, showing a steady increase in phytoplankton algal abundance as we move up in pond area. So the additional turbulence, we think, in larger and larger, more wind-exposed ponds gives rise to larger phytoplankton populations in shallow lakes and stormwater ponds. So we see kind of at either end of the spectrum, small ponds dominated by duckweed, larger ponds dominated potentially by phytoplankton, showing an increase with pond area and size. So what's controlling duckweed abundance? That is I know it's a burning question for you, much as it is for us, because you've seen all of this information about duckweed. Well, what's controlling it? We know that it is hungry for nutrients. Nitrogen as well is sometimes a limiting nutrient for duckweed, but we don't have a lot of information on nitrogen. Phosphorus, we can see some pretty strong patterns here across ponds in our database. Ponds with higher phosphorus, if they cross a threshold, we begin to see duckweed becoming highly abundant, reaching 100% cover or all of the pond dominated by duckweed. But also at high phosphorus, we have a lot of ponds that don't have duckweed. And so there's a second factor that is evident here, and that is wind. So these free-floating plants are pretty easily shifted around by the wind. And so at higher and higher wind, indicated by fetch, so Ben Janke talked about the great work that he did to analyze different ponds, and I hope you all remember that from yesterday. I'm sure it went by fast. I won't sort of repeat that here, but increasing fetch is larger ponds, less sheltered ponds. So we have a normalized metric to take into account the local sheltering around ponds as well as the size of the ponds. So ponds with larger, bigger fetches get lower duckweed persistence. They just can't hang around in windy environments unless they're like stuck onto some emergent macrophytes, which you sometimes see in shallow lakes. So check out Battle Creek Lake this summer as you're driving by. You can see this in action. But usually, or on average, duckweed then is limited to the small, more sheltered side of the spectrum, requiring a lot of nutrients. Okay, so looking at these two different communities, phytoplankton, duckweed, or three different communities, and submerged vegetation, putting together a lot of data for ponds and expressing it in this plot as the surface total phosphorus concentration in milligrams per liter. We are up in the hyper eutrophic end of the spectrum here, 200, 300 micrograms per liter, 400, 500, that's really high. For context, so we're expressing a gradient on the x-axis of phosphorus related to the coverage of the pond by free-floating plants, duckweed and watermeal. And what we can see here in this plot hopefully is sort of helpful for context. So we get the highest phosphorus concentrations at highest duckweed cover, suggesting a feedback, this feedback between anoxia and redox sensitive phosphorus release. But we also have a lot of ponds that have low duckweed cover and high phosphorus, and these are our windy, less sheltered ponds that are dominated by algae. All right, so here is some labels about the vegetation communities that we find in this space phosphorus duckweed plot. Small ponds dominated by duckweed, high phosphorus. Larger windy ponds, wind-exposed sites dominated by phytoplankton. At low levels of phosphorus, we have SAV-dominated sites, submerged vegetation, which is better able to handle pulses of nutrients coming in to a point. If we have too much phosphorus, if we cross a threshold for rapid growth of duckweed or phytoplankton, we're going to push these ponds into a different state, an alternate stable state. I refrain from calling these stable state conditions. These ponds are super variable, and we're not really sure that we're going to expect to see stable states or maybe persistent, very stable states, given all of the noise that these stormwater ponds see. Climate variation, large storms, pulses of warm water. But this is giving us I think some good information for a target to reduce phosphorus levels below in ponds to a point which we can expect submerged vegetation to be more effective, more abundant. The message here, the take-home message, we can't overload ponds with nutrients, so excessive nutrient loading is going to push things over this, what we think is a threshold in nutrients in stormwater ponds. So the question is, how do we get there? And the next part of the talk is going to try to look at this question to some extent. Many more talks and more information to come in panel discussions. Shifting gears to thinking about design a little bit, management a little bit, and some of the properties of ponds that influence both vegetation and water quality functions. So that we have a lot of goals for our stormwater ponds, as we heard about yesterday. Again, the focus is on phosphorus here. There are other things that matter and come into play because people are involved in managing these ponds, including residents and homeowners, and that is something that we need to take into account for some ponds. We have a lot of potential methods for manipulating vegetation, reducing nutrients, trying to hit control nutrient inputs or availability within ponds. And we don't yet, I think, have a complete consensus in terms of effect and especially cost effectiveness and context for using these individually or in conjunction. So the stars here on this list in the middle is there's indicating ongoing research in all of these areas. So we're still have a lot to learn about some of these different approaches, and you're going to hear more about them later on. So this is a big challenge. I'm going to start off thinking about management in terms of looking at information that we had in the database that we pulled together with Jack Distel's help in doing this. Couldn't have done it without him, in terms of looking at the different management going on in ponds, not necessarily because we think these are effective things to do, but they're happening in ponds that are used to treat stormwater. So we had a lot of information for these three things: fountains, herbicide treatments. Does that seem like a good idea based on what we've talked about? Probably not. You could probably guess that. And then last, alum, which you're going to hear about later on this afternoon. I won't say too much about it, except to say that it seems to work well. We have happy submerged vegetation communities in alum-treated ponds, so we have a growing number of ponds to look at. This comparison of managed ponds here showing the effect of, or the phosphorus concentration in herbicide-treated ponds, and fountains showing a lot of phosphorus swimming around in these ponds. So these are aesthetic management practices. In some cases, they are requested by residents. In some cases, they're applied by municipalities. But they are, in terms of herbicide treatments, sort of may be providing some visual benefits, but they're not providing any water quality benefit at all. And then in comparison, the information I showed you before for the different vegetation categories. So more on alum later on in the afternoon. To think a little bit about pond design, the patterns that we're seeing. Again, lots more work to sort of really look at the ponds that we have in the context of the design that they were built for. Most of the ponds that are in our database are older ponds that are modified wetlands, or we don't have design information. So a new project that we're starting is going to go after this information for ponds. I'll say a little bit more about that later on. And a motivating question here is one that you're all familiar with. This came up yesterday. We build a pond. We know that it's going to change and age. Over sort of long-term, a stormwater pond that's constructed will turn into something else and eventually terrestrialize. But at the short time scale, we know that predicting the rate of aging of transformation from a pond that works pretty well, looks okay in terms of water quality indicators, to one that is not providing benefits is a really important question, and we just don't have a lot of good predictive ability yet, or I don't. Maybe some of you do, but this is something that we're interested in learning more about. So I'll just share a few examples of what we're seeing, some examples, and the idea here around what we're seeing is that if you build a small pond, a shallow pond, it will age quickly. Here is an example from the city of Egan, and we got tipped off into this site by the city staff. So a new development, 2013, under construction. 2022, the image on the other side shows, about a decade later. I think you can see that all of the ponds that were constructed light up because they're all covered in duckweed, and that is an indicator that things are not so great in these ponds. You've heard a lot about duckweed. We can predict that these ponds are anoxic. We haven't been to these ponds yet, but we're gonna get out there this summer and take a look if we can. So in about 10 years, we've transitioned these ponds to ones that are dominated by this plant assemblage that has negative effects on pond function. Another example comes from the Bell Pond, which is a pond that we have been able to follow since it was constructed in 2017 on the University of Minnesota campus. So here there's a picture in 2018 in the spring. Looks pretty good. Pond was built for water quality purposes as well as educational and outreach purposes as well, in terms of providing habitat and learning opportunities for kids of all ages and adults. So it's great to have a pond on campus here like this, and we started collecting a little bit of data early on and then realized this is really interesting. We need to get our act together and really do a good job collecting information, because this pond changed incredibly quickly from one that looked pretty good to one that was dominated by a transient submerged aquatic plant, a potamogeton, filamentous algae, big cladophora bloom, and then by 2022, watermeal and duckweed show up, the pond goes anoxic, things are falling apart pretty rapidly, and then cattails. So this is, if you're interested, you can see a time lapse from the chronolog site here for the Bell Museum, showing the dynamics of growth of cattails in the pond. And this is necessitating land care at the university to get in there and try to manage cattails. And I think if you had told the Bell Museum folks what they would get if they built this pond, they would probably choose a different design, I'm guessing, because it's an incredible amount of effort to try to push this pond back to something that they want. Water quality benefits may still be there, some of them at least, but certainly things like biodiversity not, and access to the pond for aesthetic purposes is no longer there without intensive whole pond cattail removals, which they're doing. Last example, we know ponds, some older ponds do work well, and here's 3 examples. We don't have much information for these, like most of them 1 or 2 visits, site visits, but these ponds maintain in 15, 20-year-old age, they maintain good water quality functions, at least indicated by phosphorus. There's a ton of salt in them. That's another issue. And maybe now you can guess which of these ponds is 600 feet away. You can't see the Home Depot sign, but if you go across the street to the Home Depot, you'll find the pond at the top. It has hung in there since it was built. Looks pretty good. Again, we don't have a lot of information. So what do you see? What do you see that might be different from some of the other ponds that we've looked at? No trees. So it pains me to say this, but not having trees around, having lawns, maybe is a sort of a helpful thing in this context, right? So more work to be done, but the pattern here I think is emerging, and I think it is a solid one. Ponds that look like this, they also have watersheds without a lot of trees, so there's probably less nutrients and organic matter coming into them as well. But these are the types of ponds that seem to be doing okay over longer periods of time. So they're deeper. All of these ponds are at least 6 feet deep or more. They do have a lot of salt in them, but sort of lower tree abundance locally and in the watershed as well. All right, for the last part of my talk, I'm going to talk about some management maintenance experiments with the city of Bloomington, and Jack told me to encourage you all to do these things wherever you are because they're fun, they're informative, and we need this type of information. The first experiment is a duckweed removal experiment to try to get sort of more directly at the impact of duckweed. I won't talk about the experiments that didn't work in the previous year, so we resorted to this design, the split pond design in the Canterbury Oaks Pond, which you'll see in the second example as well. So we, Jack and company, manipulated this pond by moving all of the duckweed in the pond over to one side of the pond and keeping it there as best we could, and then reducing duckweed on the other side of the pond and maintaining this for 6 weeks or so, as long as we could, recording all of the things that we do in intensively monitored ponds. And what this did is increase subsurface light, as you can see here. So we're removing that reflective duckweed layer, improved oxygenation, and some experimental results looking at native submerged aquatic vegetation growth, substantial improvements in submerged vegetation growth when we remove duckweed from these ponds. So we get a boost in submerged plant biomass measured, and we did this with these phytometers here, which is a glorified term for plants sort of velcroed to this a PVC pipe and submerged in the pond to measure their growth rate over many weeks. So we see a sort of really another piece of evidence sort of showing the negative effect of duckweed on submerged plants, which is another mechanism that affects oxygen as well. All right, and so I think one interesting thing to point out is Jack's poster as a way to turn the tables on duckweed a little bit, if you will. Duckweed has a really high phosphorus content. If we can harvest that biomass as a maintenance practice, we can get a pretty cost-effective way of removing as a harvesting practice, removing phosphorus from ponds that are overly enriched in phosphorus. So check out Jack's poster. If you haven't, there's some work to be done to optimize methods to sort of make this efficient and easy to do. If you remove duckweed once, it will grow back. So this is something that's got to be implemented and optimized, but I think Jack's done some great work on this and some nice action shots from trying this out. All right, last example. The second example is a management and maintenance experiment number 2, also in the Canterbury Pond. Here's a picture of the part of the team out there looking at this pond in 2022. And we studied it in 2023, 2024. City of Bloomington has monitored this pond for a long time, so we have a lot of information about it. Then the city removed the trees, or most of the trees, around the pond, and this gave us a really great opportunity to look at the effects on tree removal as a potential management maintenance practice for ponds. So I'll summarize this before-after pictures of the pond, substantial reductions in the tree canopy. A lot of that tree canopy was overhanging the pond and probably doing a lot of different things in terms of adding nutrients directly, shading, and blocking wind. The data plot here shows where Canterbury Oaks Pond fits in our sheltering metrics. So Ben showed you this data for different ponds arranged by their fetch, their wind exposure. And what you can see is Canterbury Oaks Pond started out really on the highly sheltered end of the spectrum. Removing the tree canopy sort of helped a little bit, but In reality, this pond is set in a dense in urban environment with a lot of large trees in it. And so it didn't, it increased the wind exposure, but not hugely. So we didn't see a huge reduction in duckweed. We don't have, we're still analyzing data. But even though we saw a relatively modest reduction in duckweed, modest increase in wind, we saw a pretty substantial increase in submerged vegetation growth. So here, this is a different scale for looking at submerged vegetation from rakes. I know many of you have used this method to look at submerged vegetation. A full rake is a score of a 4. No vegetation is a score of a 0. Canterbury Oaks Pond, from the intensive sampling that we did, increased from a score of around 1 to over 2.5. So we saw a pretty substantial increase in biomass of submerged vegetation. And with that, we saw a reduction of total phosphorus concentrations from almost 0.5 milligram, so really, really high, to 1.6 milligrams, which is still high, but it's a lot lower than it was in the recent 5 years preceding. So we are seeing some benefits to tree removal, and this is consistent with some of the other information that we're seeing in these ponds. So I'm going to wrap up, sort of leaving you with more questions, some to address today, some beyond, summarizing some of the different methods that we use: alum, herbicide, mechanical removal, tree clearing, street sweeping, designing deeper ponds in unsheltered conditions. All of these sort of requiring more information, requiring information about the context and the setting of the pond, and all of them with issues remaining to be addressed still, with the exception of herbicide, which just seems like a bad idea no matter what for most things, and unless we're dealing with invasive species. All right, so I'm going to end there, and I'm looking forward to further discussions. Unfortunately, I won't be here for a lot of that, but I'll connect with everybody later on. I want to point out more information. If you want to know more about the recent project, there's a link to the final report here. And also want to take a minute to point out that we have a new project starting that is, again, focused on constructed ponds, designed ponds, and some new folks involved in that, including Jake Walsh, Sam Mice, who's here. Where are you, Sam? Sam is there. Julia Grabeau is there as well. So lots of new work, and we are interested in talking to you always if you have information about ponds or interesting study sites, especially those middle-aged ponds which are understudied in our database or underrepresented so far. So thank you for your attention, and thanks again to all of the people who have helped, funded, and put up with all of our pesky questions about stormwater pond management, maintenance, and otherwise. And thanks.